Okay, okay. Thank you very much, Javier. So I'm going to start this lecture too. And well, my goal, it will be in principle to get to the point in which we talk about the system with long jumps. But I want to do all the details that I mentioned in the previous lecture. So I'm going to try to repeat a little bit just for us to remember what is the model, what are the parameters, and what we want to do. Okay? So I'm interested in showing this hydrodynamic limit. Basically, I'm focusing in the characterization of limit points. And the model is like this. So just some small drawing in the board. So it is like this. There is a space, which is the bulk, which is this space that I will represent by this letter lambda n, which is just a space with points 1 up to n minus 1. And we put particles in, at most 1 particle per side. And after the ring of a Poisson, after the ring of a clock, which is defined by these Poisson processes, a particle jumps either to the left or to the right with rate 1/2. And we attach these, let's say, these two artificial points at 0 and n, which represent the reservoirs, and which means that particles can come in or get out of the system through the site 1 only. And the same thing at n minus 1. So particles can get in at the site -1 or get out from this site to the reservoir. And this is the rate. So there is a bunch of parameters, but it is alpha. So to get in from the left, it is alpha kappa divided by n theta. To get out, 1 minus alpha kappa over n theta. And the same thing here, but alpha is replaced by beta. Okay? And we have seen that if alpha is equal to beta to some parameter rho, the Bernoulli product measures, they are invariant. But if alpha is different from beta, which is the case that the reservoirs have a different strength, then the Bernoulli product measures are no longer invariant measures. But there is a unique invariant measure, which is called the stationary non-equilibrium measure, which I do not need to know any information about this measure in order to conclude what I'm going to conclude. Nevertheless, there is this matrix ansatz method, from which we can have, in fact, a lot of information about this measure. Okay? So to define properly the hydrodynamic limit, okay, I wrote some things. I'm not completely sure if I wrote everything in the previous lecture. So, okay, so let us fix omega n as the space state of the Markov process, which is 0, 1 to this power lambda n. So P of mu n, so when you see this double arrow, and sometimes I write the expectation with these two arrows, means it is with the expectation with respect to this probability. So it is the probability in the space of trajectories for the Markov process, starting from mu n. Then I have this measure Qn, which is the measure induced by the, okay, I didn't wrote by the empirical measure. So the empirical measure that I represent by this pi n, it is just this measure, pi n p eta du is 1 over n, the sum of x, h, x over n. Oh, sorry, I'm putting the test function. Sorry, it is not this. This is a Dirac. Okay, so this is the measure Qn, which is induced by the empirical measure starting from the measure mu n. And the measure mu n, the only thing we have, okay, I'm going to say why do I assume that, but so far the only thing I said is that we needed to take a measure which is associated to a profile, which is a function g from 0, 1 to 0, 1, which is measurable. Okay, and I'm going to try to tell you why we can take any measure. We don't have any other restriction on the measure as long except this one. Okay. And I showed, so what we want to, okay, so being associated to a profile, what it means is that this thing is true with respect to mu n. So what is this? This is just the integral of a test function h with respect to the measure pi n times 0. And this means that so it means that the measure pi n at time 0 converges to a measure which is absolutely continuous with respect to the Lebesgue measure and whose density is exactly the function that I am fixing. Okay, so this means that mu n is associated to the function, to the profile g. Okay, so the question is, if this is true at the time 0, is this true at time t? So the question is this empirical measure, is it converging to this deterministic measure, which is absolutely continuous with respect to the Lebesgue measure? And this density here is solution of some PDE, and in which sense? Okay, so that is the goal. And okay, just to recall the definition, which is exactly what I just mentioned, of what is a measure which is absolute, what is a measure which is associated to the profile. And the result is the following. So take some function which is measurable, g, take this sequence mu(n), which is associated to this function, and then we can show that the empirical measure converges to that measure, and this rho t is the unique weak solution of some PDE, which in fact depends on the range of the parameter theta. So depending on theta, we will get to different PDEs, okay? And that is what I basically explained in the last one. So these are the 3 PDEs that we get. So when theta is less than 1, which means that, so theta negative means that the reservoirs are very fast. Theta positive means they are slowed. So if they are very fast or slowed but not so slowed, we get the heat equation with Dirichlet boundary conditions. So the profile is fixed. The value of the profile is fixed at the boundary as being alpha at 0 and beta at 1. If theta is equal to 1, we get the heat equation with Robin boundary conditions. So what we are fixing now is not the value. So the profile is no longer alpha and beta at the boundaries, but we fix the derivative of the profile in this way. So you see that kappa here, this kappa that I put over there, it is the same kappa here, and it appears only in this regime for theta equal to 1. In the other two, we don't see it. And this is just Neumann. Okay, the heat equation with Neumann boundary conditions. So when the reservoirs are very, very slow, we don't have any, let's say, the profile is locally constant at the boundaries, okay? So my goal was just, to prove this, okay, so this is just a drawing with, so how do we prove the results? There are 2 things to do. One has to show tightness. So one has to show that these measures Qn, they are tight, and then we have to characterize the limiting process. So I have to say that the limiting process that I called Q star is supported, let's say, on trajectories of measures. Let me use this notation, dq, which are absolutely continuous with respect to the Lebesgue measure, and the density is the unique weak solution of the corresponding PDE, okay? Is the unique weak solution of the corresponding PDE. So this is equal to 1. So to prove this, to prove that they are absolutely continuous with respect to the Lebesgue measure is something that is general. If you have an exclusion process, it is simple to deduce it. So I'm going to try to concentrate in the part that I think it is more interesting, which is to see that, in fact, when you change this value of theta, you get a different boundary conditions from the PDE. So, in fact, what I'm going to focus is this, this second part. So, first, what is the notion of a weak solution? Somebody did the exercise that I proposed? No? Okay, so it is like this. I'm going to show, so let me just put here the result. So if theta is less than 1, we are going to show that the PDE is the heat equation. Okay, I'm going to use these letters with Dirichlet boundary conditions. Okay, for theta equal to 1, I'm going to have the heat equation, but with Robin boundary conditions. And for theta bigger than 1, the heat equation with Neumann boundary conditions. So, and as I said, the exercise was just to, okay, because I'm going to show different notions of weak solution. So the exercise was to do the following. If you take the heat equation, okay, so let me put T and Q. And now we take a test function h without saying what type of boundary conditions this function has. So I take a function h, I multiply both sides of the equation. I make an integration, a double integration in space and time. Okay, here. The integral from 0 to 1, the integral from 0 to capital T, let's say. In fact, I should use S, but whatever. So here there is a dq dt. I do the same thing here, make an integration by parts, okay? And if we use the fact, so this is Dirichlet, and I'm going to use this notion, which is for test functions which are continuous in time, so C1 in time, C2 in space, but they are 0 at the boundaries, okay? So if we use these boundary conditions here, that h0 is equal to h1 is equal to 0, So when you make this integration by parts, you will see that there are some terms which should appear here, which depend on the value of the function at 0 and at 1. But since they are 0, they don't appear, and we get this. OK? And I'm going to use this notion of solution. So I say that this is true for any theta less than 1. But in fact, I'm just going to use this notion of solution for the case in which theta belongs to 0 and 1. OK? In the case where theta is negative, so it is the case, so this is, so when theta is negative, the notion of solution that I'm going to use is the next one. So, I mean, there is always this, OK, in the previous, so you see that in the previous one, I just asked two things. The solution has to be in some Sobolev space, and it has to satisfy this integral equation for this special space of test functions, which are 0 at the boundaries. The next notion of solution that I will use for the same equation is that the rho has to be in some Sobolev space. It satisfies the weak formulation, but now my space of test functions, they are of compact support. So if they are of compact support, you see that this term here, these derivatives are 0, so I don't see these terms in the equation. Okay, so we don't see the alpha. We don't see the alpha and the beta in the integral notion, in the notion of weak solution. So I need, in order to have uniqueness, I have to ask this extra condition, that the rho t is alpha and beta for any t between 0 and capital T. Okay? And this is the notion of solution, okay, that I will use in the case where I have the fast reservoirs. Then, when theta is equal to 1, we have the, okay, maybe I should write it down. So the Robin boundary condition means that dq, okay, and just to recall, this q is my macroscopic space variable, okay? So this dq, rho t at 0, is going to be kappa, rho t at 0 minus alpha, and dq, rho t at 1, is going to be kappa, beta minus rho t1. So these are the boundary conditions that we have for kappa equal to 1. And for kappa bigger than 1, just take it is equal to 0. Okay, just take kappa equal to 0. So doing this trick that I said, you just multiply with a test function, you integrate, and you use the boundary conditions, you get this expression here for the solution. And in this case, I ask the test function not to have any kind of boundary condition. Okay, just a function which is C1, C12. Okay? And the goal was to look at the particle system and try to see how to make how to force one to have this expression for the limiting solution for this rho t. Okay? So I said that, okay, we are going to apply Dynkin's formula. So we are going to apply, there is this result, and we are going to apply it for this function ft eta t, which is in fact just a function which depends on eta t, which is the following. It is just the integral. So it is my, okay, I'm going to use this notation as I used before. So this means it is the integral of a test function h with respect to the empirical measure. Okay? So this means that this is 1 over n, the sum of x going from 1 to n minus 1, hx over n, eta t n squared x. Okay? I'm going to use it with this function, so I know that I have this expression. So I have that m nt at h. So let's not impose anything on h by now, okay? Just take a nice function h. So according to this result, I know that this guy is a martingale, so this is pi n at 0. And in fact, let me take a function, or maybe not. For now, I'll just take a function which depends on space. And at the end, I will say, if it depends on time, what do we have extra? Okay? So h does not depend on time. So so I don't depend on time. And the integral from 0 to t, so this term does not appear here because my function f does not depend on time. And now I have to compute these. ds. And in the last lecture, I just put the expression. So now I'm going to try to explain how to get this term out of here, okay? Because it is a term that depends on the dynamics. Okay, so I say a simple computation shows that. So let's compute this term here, okay? So Ln. And remember, do you need me to write down the generator? You remember? What do you think is best? Should I write it down? No? No? Okay. So I'm going to use the computations that were written in this board the last time. So let me try to remember. So we have pi ns at h. And since this is 1 over n, so when I do not write the sum, when I do not index it, it means I'm looking at the bulk, okay? So this is h x over n. And now I have to compute the action of the generator in this eta s. Okay, sometimes I will forget the time scale, but the time scale is always written in eta, okay? X. And now we have, from the computations that we did in the morning, that Ln of eta 1, remember that I wrote this as the difference between currents? Yes? So there was here eta 2 minus eta 1, which was the part that the generator in the bulk was acting on eta 1, yes? Plus kappa over n theta alpha minus eta 1. Yes, I don't put the time, so it is this. Okay? Then, for all the other, let's say, eta z, z different from 1 and n minus 1. So for n minus 1, I'm going to write it in orange. So it is like this. It is exactly the same. Here it is n minus 2, n minus 1. Here it is beta. And here it is n minus 1. OK? Yeah. So here what we had was the eta z minus 1 plus eta z plus 1 minus 2 eta z. OK? So now I'm going to put this thing here. So then I have 1 over n. So I'm going just to expand it to make it simpler. So I have these times that one. So eta 2 minus eta 1 plus kappa over n theta plus 1 over n h So what I'm doing, no, it's wrong, it's eta 1. And here I have eta n minus 2, eta n minus 1, kappa over n theta, beta minus. You agree? Yeah? I'm just expanding the sum and replacing the ln at eta x by these expressions here. Okay? So now, the idea is to somehow close this equation. And what I mean by that is that I want to write this term which is here in terms of the empirical measure, as the empirical measure applied to some function. Okay? So now, let me isolate the terms in eta 1. So then I have, okay, these guys, I'm going to put them separately. So I'm going to have 1 over n, h at 1 over n, yeah, minus, plus 1 over n, h2 over n. And now I collected this guy and this guy. Do you agree? Yeah? So I have these. I'm forgetting the times, yeah, I'm forgetting the n square. So there is an n square. You see this n square? I forgot to put it, so I have to put it here. An n square, and there is an n square. And now, okay, these ones I will put at the end. So then I have plus n squared, and the guy is in eta 2. And in eta 2, there is this one, there is this one. There will be another one in the expansion for h at 3 over n. Okay? So then I will have h 3 over n plus h at 1 over n. Okay? And the same thing everywhere for the other terms, plus the last one for eta n minus 1, And the boundary terms that I'm going to circle them, which are these ones, and this one. Okay, this one will be separate. And here, what I have is what? Okay, there is this term here, so it's going to be minus h at n minus 1. Am I forgetting the, yes, I'm forgetting the 1 over n. You see here, there is a 1 over n missing. You see, I forgot it, sorry. So there is a 1 over n here everywhere. So there is this 1 divided by n. And for the, so if I look at the h at n minus 2 over n, so if I write it here, then I would have eta at n minus 3 plus eta at n minus 1 minus 2 eta at n minus 2. So there is another term here, which is this one. So I put here a plus h n minus 2 over n with a 1 over n. You agree? Didn't make any mistake? No? Plus these guys, okay? Plus the green guys, which I didn't write. Okay, so now, can I erase this one? Because otherwise I will have to go to the other one. Can I erase this one? Yeah. So now, I'm going to do this sum and subtraction of the terms that I need. So I do the following. You see that in eta 1 and in eta n minus 1, I do not have the discrete Laplacian of the function. Right? So I'm going to sum and subtract the terms that I would need in order to have it, and then I will control the rest. So to have a discrete Laplacian, I'm going to sum and subtract h what at 1 over n, okay, 1 over n, h at 0. And I will do the same thing here. So I sum and subtract the h at n minus 1 over n minus h at n over n, which is h at 1. And there is a 1 over n, which is missing. OK, so now, to get to the Laplacian here, because you see the first term that I wrote there, it is the empirical measure applied to the discrete Laplacian of h, the first term which is here. OK, so let me write it. This term is coming from, so to have the discrete Laplacian here, I have to use this. I'm going to circle means that I'm using this guy, okay? So if I use this, I have exactly the discrete Laplacian of h at 1 over n. Here it is already nice in the bulk, not in the, in the points which are not 1 and then minus 1. And here, to have the discrete Laplacian, I'm going to use the minus as well. Okay? So now this means that I have pi n, there is no time, but there should be a time, h. Oh, sorry, the discrete Laplacian of h. So the discrete Laplacian of h at x over n is just n squared h plus 1 over n, h x minus 1 over n. And now we still have the terms which have the plus in orange and these two terms. So the terms which are in green over there, so let us check that it corresponds to these ones. So the first one you see there is a 1 over n, h1 over n kappa divided by n theta. So you see this term here, it is exactly this term. Okay? This term here, it's the last one. Okay? And these ones, with the plus, are these two here. Okay? So this is what we get without imposing anything on h. So now, okay, maybe I write the full expression. So dt is plus the gradient plus at h0, eta s n squared at 1 minus hs at 1. Okay, my h does not depend on time. True, okay. And I have this eta s n squared n minus 1. Can I erase the Laplacian? Can I erase this Laplacian? Yeah, because it's in the middle. Yeah. and then plus kappa n1 minus theta h1 over n alpha minus eta n squared at 1 plus kappa Okay, so in the Martingale, so when we go back, when I look at the Martingale, so I have mnt at h equal to pi nt at h, pi n0 at h, minus the time integral of this guy. I'll put it here, okay? So now I have pi ns of this guy minus the integral in time of this term. There is a plus eta s n squared at 1 minus this term at 1 minus the integral from 0 to t of this last one. I'm just going to write 1, okay, because the other is exactly the same. We just replace 1 by n minus 1 and alpha by beta, okay? So I will put here some extra, but it is that one. Kappa n1 minus theta h at 1 over n times alpha minus this thing. So if we want, okay, plus the other guy, I put a star. So if we want to get, so this is a Martingale. And if we want to get Dirichlet boundary conditions, so let us remember, yeah, this notion here. I have to see how to get it from this PDE, how to get it from this Martingale. In the limit, when I take the limit to infinity, of course I'm going to say that some things are true and I'm not going to show it. But how to get these terms, okay? So I say if h is 0 at the boundaries. So let's look at this term, because you see this term doesn't appear in the equation, right? So there is the first term. There are these two first terms which come from here, this one and this one. The second term with the Laplacian, and you see if I take a test function which also depends on time, there is an extra term, because if you remember in this Dynkin's formula, there is this term here. So if I put this derivative in the Martingale inside this integral term, what we have is the pi ns. So if the function depends on time, the only difference is that I have this extra term, and of course everything depends on time, okay? So a function depends also on time. So then, what I say, yeah, so we have this. Oh, sorry, I want to put the PD. Yeah, it's this one. So if the function is 0 at the boundaries, I can come here and transform this n, h1 over n, as the discrete gradient of h at 0. And since this is of order n to the power minus theta, if theta is positive, this vanishes. You agree? So I don't see this term. This term disappears. The other one is exactly the same. I complete it with the h at 1, which is 0. So I transform this times n into a discrete derivative, and it vanishes for theta positive. And then it remains this term and this term. But in the equation there, you see that in front of the derivative, for example, this one, this partial derivative at 0, I have an alpha in front of it. So what I will need is what is called the replacement lemma. Can I erase this one? Yeah. So I need to show, and this is the goal, this is what I want to do today with all the details, is to prove that we can in fact replace, so I'm just going to write it naively, I can replace eta 1 s n squared by alpha, okay? And the same thing for the n minus 1, I can replace it by beta. So if I do that, then here I would have an alpha, here I would have a beta, and when I take the limit, I should get exactly these two terms. Okay? This term which is here and this term which is here. Okay? So so this is what I say. But you see that, so this is what I say in this slide. I have to do this replacement. And somebody asked me, I think it was you, asked me if this was true for any theta. And no, so this replacement, to replace this eta 1 by alpha or this 1 by beta, only works for theta less than 1, okay? So we get to these, and now we get to the terms which we see in the PDE, okay? Theta less than 1, yeah. Sorry? Yeah, this replacement that I'm writing with this, see? I mean, replacing eta 1. In fact, it is not this. It's the time integral of this. I will show it. I will prove it, in fact. Over time, yeah, over time. So the integral in time of, so what we are going to show, to be precise, is that when you start the system from any measure mu n, okay, with that restriction over there, it has to be associated to some profile. But anyway, this result holds for any measure, and you prove that. So this is what I want to do in 5 slides or something. Okay, we will start with the proof of this. So this is what we call the replacement lemma. And the same thing is true if you take n minus 1 and beta. But this is only true for theta less than 1. Yeah, the reservoirs, if they are very, very slow, and theta equal to 1 is like the borderline, you don't see, you start not to fix the profile at alpha. So you cannot actually replace it by, you cannot replace it to 1 by alpha. But you can replace it by something else, and I will explain what. Because, okay, so this is for Dirichlet. It is clear that we need to do something to see this alpha and the beta, yeah? But I said that we take a function in this, with these boundary conditions, and somewhere, which was here, I said, we transform this into a discrete gradient, and then the error is of order n to the power minus theta. But if theta is negative, this n minus theta is very big. So the way to control it, and this is why I have these 2 different notions of fixed solution, is to take a space of test functions in which you don't see these terms. Okay, so here, remember, I have a discrete derivative of h. So if I ask the function to be of compact support, and this is the reason why there is the second notion. So you don't have these terms. So in fact, you don't have none of these terms. So you have nothing here in the equation. You just have the term which comes from the Laplacian. So there is nothing to do. You see, there is no replacement lemma because everything is closed. So functions of compact support, can I erase it? Yeah. For functions of compact support, you don't have these extra terms. So this is your Martingale. And everything is nice now. One can take the limit and see, of course, taking the limit, there is many things to do, but okay. You see that you only have, let me just go back. No, it's not this one. So you have exactly what is written here. Okay, this extra term comes when we take the function, which depends on time, okay? So you have these. But now, to have the uniqueness of the weak solution, we need to show that the profile is alpha and beta at the boundaries. And this is another replacement lemma that is needed. So in that case, what you need is not this one, but in fact, they are, I mean, the way to prove them, they are very close. So the other one, in that case, is this one. So this is for theta less than 1. And this one, can you see? Is it okay? It's not messy? No? So we say that the integral from 0 to t, I'm going to say what is this notation because I think it didn't appear yet. So 1, or maybe Sn squared. So this is what we have to show. Yeah, this is the limit when n goes to infinity. And here is more. So what is this? So this means we are averaging over a box. So if I have eta L, at 1. This is the average of particles in the box starting at 1 with L sites. So this is just 1 over L. The sum when x goes from 1 to L of eta x. Okay? And for Robin or Neumann, because they are very similar, so the notion of solution, maybe I should write it, maybe here. So the notion of solution, I erased. I didn't want to erase. Okay, maybe I know what was here. Is the integral from 0 to t. Was what? Okay, I don't want to erase because I want to recover it. So it is the gradient at 0, eta Sn squared at 1, minus the gradient at 1, plus these extra terms, kappa n 1 minus theta, and the same guy, but for the, for the other reservoir, okay? So we have this. But for Robin, the notion of weak solution, and I don't want to erase this as well, and no. Okay, so maybe I should put here the notion of weak solution. Yeah, this one. So how to see this from these terms? So let's take first theta equal to 1. So theta equal to, and H has no boundary conditions at all. I do not ask anything, okay? Just a function C1 in time and C2 in space. So theta equal to 1, it is precisely the value which kills this term. This is 1, okay? So this, okay, here, this term, if you see it in the equation, I say it corresponds to something. So let's look. H1 over n, it is this term here, okay? So this term for theta equal to 1 will be kappa H1 over n alpha minus eta S1, this guy. So I need a replacement lemma which allows me to replace the value at a point, so the eta at 1, by the average in a box. So in fact, it is not this replacement lemma, but I will need, okay, in green, it's theta equal to 1. I need to replace this guy not by alpha, but by this. Okay? And you ask me, but why do you need that? Because this guy now, if you look, this is the definition. Okay, epsilon, L there is epsilon n. And this is somehow the integral of pi nt applied to an indicator function over the interval 0 epsilon. Okay? So somehow, if you believe, this guy, this eta epsilon n 1, and here is a time, is close, in some sense, to the row S and at the corresponding macroscopic point. So this is a point in the bulk, 1, and macroscopically it corresponds to the point 0. So I can, if I am allowed to do this, to show this, which in fact is true, okay, in green, for any theta greater or equal to 1, we can replace this. So if this is true, then I can replace the eta 1 by this guy. So here I replace this guy by the average over a box, and then the average over a box is close to this row S at 0, and I recover what is written over there. The same thing has to be done for the other guy. So everything I say for the left, the same thing has to be done for the right. So we also need the same thing, but for n minus 1, so that you replace the eta at n minus 1 by the average to the left. Okay? This is technical. I will try to give you the proof with all the details. But then we already recognize from here this term, and this term here, you see, it's exactly the same thing. Here, this goes to the derivative of the space derivative of h at 0, and you need again to replace this guy by the average. But that is exactly what you need for the second one. Okay, for this one. So it's okay how to get what one needs. So it seems like, it is a symmetric simple exclusion, there is nothing to do, but there are these replacement lemmas that one has to do to recover exactly the boundary conditions. Okay? So, is it everything okay, or? Yeah? Can I go to the proof of those? Yeah? So let me just go quickly over. So I said, as I said, so just to theta less than 1, between 0 and 1, you need this replacement lemma to get the alpha and the beta out of the equation. Sorry, okay, so this is just what I say. So, okay, so the way, because I say, you take the limit. So heuristically, let's say, not rigorously, what you do is that you have this martingale, you apply the expectation with respect to mu n. When you apply the expectation to this guy, you get this. I said what is this guy in the morning, but let me just, so this rho nt at x is the expectation with respect to mu n of eta tx. So when you apply the expectation to the martingale, well, the martingale, the expectation is constant. The martingale at time 0 is 0. So here is 0. And this is what you get. So now you suppose that this guy is close to the solution, to the rho t at x over n. And what you get is this. So the difference between these and what we wrote for the notion of a weak solution to the PD is that the h here does not depend on time. If it depends on time, then you know there is this extra factor with the derivative of s of h. OK? OK. So for theta less than 0, as I said, you kill the bad terms that we don't know how to replace. You have these, but then you need to show that replacement lemma to fix the value of the profile at the boundaries. So you need the replacement lemma, which is written in pink. For theta equal to 1, you do the same stuff. You have all this martingale. You try to replace this guy by the average. And then you see exactly, well, if you assume that the convergence is true, you get exactly what is written in the PDE. And the same thing for theta less than 1. So the difference you see between theta equal to 1 and theta bigger than 1 is that you don't have this term. Okay? It's like kappa is 0. OK, so now the replacement lemmas. I just wrote these two, but in fact, we need the extra one, the one for functions with compact support. OK? So I'm going to try to give you the proof of this one. I will leave the proof of this one as an exercise, but I will tell you more or less how to do it. OK? So let's fix on this one now. Let's try to show this replacement lemma. Oh, it's here. OK, maybe now I can go here. Can I raise this board? Yeah. OK, so now the replacement lemma. So we want to show that for any time t, the expectation, so this is the expectation with respect to the p of mu n. Okay, when I use these double bars, it means that it is with respect to this measure of the time integral from 0 to t of this guy minus alpha. It goes to 0. OK? So now I have to look at my notes. Yeah, because I'm probably going to be lost. So let me see. Yeah. So how to do it? Replacing by alpha. So the first thing I say, so this is the proof, is that I'm going to use the entropy inequality. So I'm going to do this. I said that I use entropy and Jensen, so I'm going to do it step by step. OK, first entropy, then Jensen. So entropy inequality says that, let me use this notation. This is bounded by 1 over b log. So mu and pi are measures. I want to apply it with mu equal to mu n. And pi is a certain measure. And I will just say who is this measure now. So this is this exponential of bf plus the entropy. So I want to apply the entropy inequality between the measure mu n and the reference measure that in principle I don't know what it is. So I'm not going to assume it is because remember when alpha is equal to beta is equal to rho, the Bernoulli product measure with parameter rho is invariant. But if alpha is different from beta, it is not, remember? So I'm going to try to do it general. I'm going to get a Bernoulli product measure, but which gives the following weight. So, okay, it's a messy notation. So h is a function in 0, 1, and I have to impose conditions on this function, okay? So by now, I do not say anything, and in the middle of the way, we have to see what we need to conclude, okay? So I have this function. Then we have to impose if it is smooth, Lipschitz, whatever. But then we will see in the middle what do I have to impose to kill the bad terms. So I have this measure, which means that it gives the weight. So this is a Bernoulli product measure, but instead of giving, rho, 1. With x is not rho, it's 1, so 0 or 1. So the weight of this is just h at x over n. If h is constant, is the usual one that we see before. If not, it is this, okay? Which is not an invariant measure. So I'm going to apply the entropy inequality because somehow I do not know anything about this measure except that it is associated to a profile. So I need to change for a nicer measure. And let's see what do we get with this one, okay? So applying entropy inequality, we have, where is it? It's here, okay. So I'm going to do it carefully. So I have the expectation, mu n. I'm going to forget the time scale, okay? But everywhere where it should be the eta s should be this guy, okay? Just not to write it all the time. This guy, I'm going to write it as the integral over d mu n of the expectation of eta of this guy. Oh, sorry, it's messy. Can you see it? Can you see it? So it is just, this is the integral with respect to this measure, and I just split it into the integral by mu n, and then I integrate. So this is the measure for the Markov process starting at eta, the configuration eta. And then I average with respect to the mu n. Okay? So now I apply the entropy to replace the mu n by that measure over there. So now, and b is a constant. I didn't say, but b is a constant, and it is important. But I will say it at the end. So this guy is less or equal than the entropy of mu n with respect to the mu n h. And I want to do some trick, which is to multiply and divide by n. So you see, it does not affect anything, right? I just multiply and divide because it's going to be useful, just because of that. So here I do the same. I have an n here, and I have a 1 over n. Okay? So now I have here this guy. I have, didn't I forget a b? No? Okay. So here I have an n, and here I have 1 over n. So this n that I'm putting here is this guy which is out. Okay? And here I have 1 over n times b, the log of the integral. The integral of what? Exponential times the function. This is my f. You agree? So here I have b times the exponential, there is an n with t. Yeah, the log of this thing with respect to d mu h n. Okay? Is it okay? Yeah. Parentheses are wrong. So now I use Jensen. So by Jensen, this is bounded by the exponential, okay, maybe I can write it like this. The exponential of Bn integral yeah, okay? Yeah? Okay, so what I say, yeah, I forgot a B. Yeah, I think here there is a B missing. And here there is a B. So now I say, okay, I have this expression, 1 over n log, blah, 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 okay. And now I say, okay, B is a positive constant, H is a profile to choose later on. And then what I want to do is to remove this absolute value from the expectation, from this exponential, sorry. So I use the fact that this inequality is true, and that the lim sup of the log, yes, in fact, I'm going to show that the lim sup goes to 0. So this, to be precise, is the result. The lim sup goes to 0. And then, first computation to do is to compute this entropy here. And I say that this entropy, whoever is the measure mu n, this is of order, so this is bounded by a constant, which depends on alpha and beta times n. Okay? Okay, so to compute this, we can write this as the sum of a eta. So there is a mu n of eta. You bound this guy by 1, so this guy disappears. And then, okay, I leave the rest as an exercise. You conclude this, C alpha beta n, and you use the fact that you know explicitly who is this measure. It's a Bernoulli product measure, which gives weight, this weight here. And you just use the fact, and this is the first restriction that we need to have on the function h. Okay, because at some point you're going to have nu h n at eta. So what is the weight of this configuration? It is going to be eta x over n to the power, the product of x of eta x, because if a particle is occupied at the site x, it gives the weight hx over n, okay? Times 1 minus hx over n, because if the site is unoccupied, you give this weight to the particle, right? So this is the product over x, 1 minus eta x. And at this point, I need to have this condition on h. You see this first condition here? It is bounded from below and from above by alpha and beta. So let's suppose alpha is less than beta. Okay, and with this, you recover this. Okay? So here, so far, so here we are going to have a constant. So you see the reason why I needed the n over here, okay? So here there is a c alpha beta times n. So these guys disappeared. So if at the end I do everything and I have the freedom to choose b, then at the end my error, if it depends on b, I just take b to infinity. Of course I cannot have 1 over b and b, otherwise one goes to 0 and the other one blows up. But if everything is fine, if I can control this guy, with n, then at the end, I take b to infinity and we're done. Okay, so now let's focus on this guy. So now, I apply the Feynman-Cox formula because it gives, you see, okay, this is quite general, and I'm going to apply it with this measure nu. You see this measure here. So I know that I can control this guy by the exponential of the time integral of this term here, which is given as a variational expression for it. And then we have to solve this variational problem. Okay? So at the end, I say, then we have to estimate, okay, so now, okay, can go this way. So I have 1 over NB, the log, cannot see, the expectation of the exponential, cannot see, Bn times the integral. There is no absolute value. Yes? Okay, and then I apply the Feynman-Kac formula, and I get to this. So, okay, so now this thing is bounded by, you see there is an exponential of a time integral of this gamma s. So when I have the log out, the log and the exponential will give me 1 over Bn times this sup over f. Okay, of who? So now I have the integral of eta 1 minus alpha times f of eta with respect to this measure. And there is a b times n, sorry, here. Yes? Plus this other term, which is here. And the generator for us is n squared. So I'm going to take this, but you see, instead of taking a function which has L2 norm equal to 1, I'm going to take it with respect to a density, and I'm going to take the square root of it. So instead of having there I have the f to the square, and here I have f, and here and there I have the Dirichlet form. This is called the Dirichlet form, but applied to f, and here I'm going to have the square root of f. Okay? So I have this, and now the measure is still this measure, nu h n. Okay, so this is the full generator, our full generator, the bulk plus the boundary. Is it okay up to here? Yeah? So now, this guy is multiplying everybody, but you see that when it multiplies this term, it disappears, so it cancels, but then it appears here, so I'm going to put it like this. This is plus, so there is an n squared, there was an n squared, and I'm going to divide it by nb. And this guy, when it divides, it simply disappears. You agree with this? Yeah? Okay. So now, yes, and this is what I say. Yes, this is n over b. So now there is another hard thing to do, which is the following. Remember that we need to show that this guy goes to 0 in n for any b, because at the end I need to kill the part which has the entropy, so I need to take b to infinity. And then I say, let's control Dirichlet forms. And this is another, so what do I mean by that? This is the Dirichlet form, and since this measure is this measure with the profile, so this Bernoulli product measure with the profile, so if it was Bernoulli, if it was the Bernoulli with the, if age was constant, everything was nice. We could write this in what I call the false Dirichlet form. So the usual one in which we have the okay, there is a square root here, square root here. Usually the Dirichlet form is minus 2. It is written in this way. But in this case, since we have this measure here, it is not written in this way. So the idea is that we have to replace the true Dirichlet form of the model by another one, which is called the false one, plus an error, okay? Because, and why do we do that? Because it is easy to relate this guy or to bound this term by the false Dirichlet form, okay? So I'm going to do two things now. I'm going to show you what is the price to replace the true Dirichlet form by this false Dirichlet form. There are some computations to do. At the end, we are going to be able to replace this term here by the false Dirichlet form, which is nice because it helps us in the computations, plus an error. And this is where, again, we have to impose conditions on the profile H. And then the last thing to do is to compare this guy with the false Dirichlet form. And then we put everything together, we cancel the terms, and we show that it goes to 0. Okay? So now let's control the Dirichlet form. Yes, so it is here. So I mean by Dirichlet form, the false Dirichlet form. Okay, maybe I don't need to write it again, or maybe I do, I don't know. Maybe I should write at least one from the boundary. So let me tell you one thing which is important. In fact, here, what I'm going to do, since I'm replacing eta 1 by alpha, the Dirichlet form which is important for me is the one that comes from the boundary, from the left boundary. So that's why I'm going to keep it here. So this false Dirichlet form that I called dn0 square root of f mu. So mu is any measure, and then we apply it for our special measure that I have here, okay? Don't forget, I have always this measure here. So I say, okay, this is 1 over 2. The sum when x goes from 1 to n minus 2 of the nice term that I wrote over there. So let me call this guy, this integral, is what I'm going to call I x plus 1. Okay? This is this term. And then there is the other one. Just going to write it for the left boundary. It is this k over n theta. There is a 2. And there is this term, I1, R1. Okay, then there is the other guy, which comes from the right boundary. And this term is this one. So this is just the integral with the rate. Remember this rate that I called CR1 eta 1, which is I get in at rate alpha. If there is no particle at the site 1, and I get out at rate 1 minus alpha. Okay, this was the definition that we gave for this rate. So it is CR1 eta 1. There is a square root. I hope I didn't. No, is there? Minus the square root of f of eta to the square d mu. And remember, this is the configuration in which I flip the value of the configuration at the site 1. Yes? And this one is the one in which I exchange the occupation variables at x and x plus 1. Okay? So what I want to tell you now, the next slide, is how to replace this guy by the dn. So the dn that I wrote there is just the sum of these two Dirichlet forms, these two false Dirichlet forms. Okay? So I want to tell you how much we pay, what is the price one has to pay to replace this guy by these ones, which in principle you don't think probably it's nicer, but they are nicer for the computations. Okay? So these are the false ones. So there is a price to pay, and I need this price to vanish with n. So to do that, okay, I claim that it is possible. So the claim is we replace the true Dirichlet form, ln square root of f, with respect to the measure that we want to look at. And the price is minus n over 4b. So dn, I didn't wrote it, but dn is the sum of this one plus this one. Okay, it's the sum of the two false Dirichlet forms. So it is this one, nu nh, plus an error. And you see again that this error is good for us, because I said that we could not have an error which has a b, of order b. Because at the end, to kill the error that comes from the entropy, I need to be able, you see here, I'm just looking at this term now, but I still have this term as an error, which is of order c divided by b. So at the end, I have to have the freedom to take b to infinity. And it's still good, because you see, if everything goes fine, my error here, it's of order 1 over b, so I can take b to infinity and it goes to 0. Okay? So let's prove this. And I say that it follows on the it relies on the following lemma. And I put it with this generality because I want to apply it for two different transformations of eta. One which is the exchange, because I want to replace this guy by this one. So in one way, T, the transformation that I put there is going to be the exchange. But when I'm looking at the boundaries, I need to have the flip. Okay, so let's write it as T. So I say that this is bounded by this. So let me try to give you the idea of the proof of this result. Okay? If it is too tough, please tell me. Okay, so I'm going to try to show these. Can I erase maybe this one? And we keep in mind that there is this error? Yeah? Okay. So now I'm going to try to explain how to get these. And this is a trick which is very common. And with these, then we conclude trivially the claim is just applied to each one of the generators. How is my time? Ah, it's at 3:30? It ends at 3:30? Ah, okay. So I have to be faster. So maybe just the idea. Okay, so I have to compute this. So these brackets means the integral. C eta is a local function, positive local function. And I have to compute this. Square root of f of t eta minus the square root of f of eta. Oh, sorry. Times the f at eta. Okay, it's not mu, it is the, maybe it is announced, yes, it is announced with mu. And why do I need to do that? Because this integral, this term which is written here, so if you look at the generator, for example, in the bulk, what I have here is the sum of x, the integral, and I apply the generator to the square root of f, and what I have is the f eta x plus 1 minus the square root of f at eta. You agree? This is the guy that comes from the generator applied to the square root of f times the square root of f at eta, and I compute the integral with respect to this measure. Okay? So this is why, sorry, it's not this one. So this is why I need to compute, I need to bound these guys. Okay? This is the reason why. So to get this, so you start with this, because this is what we have. And we would like to have the guy to the square, this difference to the square. This is the false part of the Dirichlet form. So what we do is a simple trick. You just write this guy as 1/2 of itself plus 1/2 of itself. Okay? So you have 1/2, 1/2, c eta. Okay, all this term, d mu, the same thing here. And now you sum and subtract the guy that you want to see. You sum and subtract the term with a square. So let me look at my notes. Yeah, so you sum and subtract this term. 1/2, the integral of c eta square root of f at t eta minus the square root of f at eta d mu. Okay? You force it somehow, you put it there, and then you have to see what you have to pay. And then I say that this guy combined with a minus, so this guy here, one of these guys, one of these terms, let's say. There is a square root missing. When I look at this guy minus this guy, it is exactly the term with a square, but with a factor 1/2, and there is 1/4. Minus 1/4. So this is going to be minus 1/2, the guy that we want. And it remains this term, an extra term, okay, plus an extra term that if you do the computations, it is equal. So it is just, when I say you do the computations, just multiply. You see that there are terms which cancel. And what you get is exactly this. C eta minus the square root of eta to the square there's a bracket here. And now, maybe here. Can I erase this one? And now I say that we make a change of variables. So you change eta into t eta. And what you get is 1 over 2, the time integral, minus ct eta. So there is the price to pay here, plus c eta times the square root of f Another trick, which is I write this guy as 1/4 of it plus 1/4 of it. Okay? So I write this as 1/4 of this guy plus 1/4 of this guy. Yes. And in one of them, I make the exchange again. I again exchange eta into t eta. Okay, and then you do the computations, and you get that. Okay? So that is basically the idea. In one of them, change variables, change variables again. You will see a term with a 1/4 with a square, which, sorry, this is a, no, it's okay, it's okay. You will see a term with a 1/4 with a square, and when you subtract 1/2, you get the first guy, the minus 1/2. Okay? So this factor here comes from combining this term with one of the terms that comes from here. Okay? Okay, if you believe me, it is correct. So now we apply these for the two different generators. I still have some time. Okay, so let us apply this result. Okay, it's again tricky, but so you see that what we have to do, the price to pay, we simply have to compute this guy for each C. So each generator that we have, if it is in the bulk, for example, you see that this C is 1, right? Because the generator in the bulk, the rate is 1. It is this one. If we are computing this Dirichlet form for the generator from the boundary, the C, for example, in the left boundary, it is this C. So what we have to compute at the end is this guy. Okay, and there is a square here. Okay? So if you do that, so when I apply this to the bulk, to the generator in the bulk, I get the following error. So I get that this ln0f, square root of f, square root of f, with respect to this measure. So I'm going to have this minus 1/4, the nice Dirichlet form, which is the guy which is the first guy with the square, this term here. So I'm going to have this term which is the nice Dirichlet form. Okay, so there is this dn0 plus a constant C alpha beta times the sum of x from 1 to n minus 2. And if you do the computation, the only exercise to do is that in the case where you have the bulk, this C is equal to 1. So the only thing you have to compute is what you pay when you replace the eta by eta x plus 1 with respect to that measure. But since it is a product measure, it is quite simple to compute it. And what you get here is just the h at x over n minus h at x plus 1 over n to the square. Okay, so this guy which is here is exactly the term that you get inside this bracket. Okay? So when we look at the boundaries, can I erase this board? Yeah? So when we look now at the boundaries, and we apply these, and now remember that the C is a different C, is not one. So what we get, yeah, it is here. So I'm putting B for the boundary. I'm going to put just the bound for the left. For the right, it is exactly the same, okay? So it is D, square root of F, square root of F. This is less than minus D and B over 2 plus K, a constant, n theta, and here okay, I'm going to put it all. Okay? So let me see if the claim gets out now. So now we multiply this by n over b. So when I multiply this by n over b, I have an n over b here. And here I have to put an n over b. And now I'm going to assume something on h. So let us assume, for example, that h is Lipschitz. So this term here is of order 1 over n squared. You agree? I'm summing over n points, so this guy at the end is of order 1 over n. I have an n, so I have c alpha beta over b, which is the guy which is at the right-hand side of the last board. Okay, the last one, the c alpha b. Okay, and here, yes, okay, and here what do? We have this. I have to put an n over b, and I have to put here an n over b. And I have to put here an n over b. Okay, so the first thing to see is that let us take h constant. So suppose we change now to the Bernoulli product measure with constant parameter rho. What is the price to pay? Okay, that one is controlled because it's even easier. This is 0, right? But this guy, suppose it is equal to alpha. Okay, this error is 0, but here this error is constant. So in front of it, you have n over n theta, which means that if theta, and remember we have the freedom to take b to infinity at the end. So if if theta is greater or equal to 1, I can take a profile which is constant equal to beta, alpha, whatever. I can take it constant, independently of what it is. This guy is constant, but this guy goes to 0. If theta is less than 1, you see the restriction. So I need to take a profile, and I need to kill these two terms. So the idea is to take a profile which is locally constant, like this. So this error is 0, this error is 0, and what you get at the end is that one. Okay? So now, okay, so the final thing to do, so what we did now is that we controlled this term here, remember? And now I need to compare this term with the nice Dirichlet form. The false, but the nice Dirichlet form. So how do I do it? Okay, so I say that, so far we have to bound this supremum over there. And I say, to finish, I compare this term, which is the guy which is over there. So this means that there is a constant in front of everybody. I don't want to take care of the constants, I put this. And I have this term, which is related to the false Dirichlet form in the left boundary, plus again, a term A. And the choice of A is the one which is giving me the error. Because if you see, if I put this guy over there, the error is 1 over A, this guy, plus A, and this guy is 0, because I take the profile which is locally constant. So my choice for A is going to give me the error at the end. And now, what we do is that let's choose a proper A in such a way that this term cancels with the part from the Dirichlet form from the left. Okay? So, to end, I say, I have I, what is the notation I used? I1, R1, over A. This is what I have from this side of the equation. In the variational formula, this guy is here. In the other side, there is a minus n over 4b times the Dirichlet form, the dn. But remember that the dn is the sum of these two guys, so this guy I just throw it away because it is positive, so I just neglect it. And this term here, there is a kappa over n theta. Okay? So I'm going to replace it. There is a kappa over 2n theta times the same guy, right? You agree? That I can just forget the other terms because they are positive. There is a minus in front of it. I just throw them away. Yes? So now let's try to choose an A, which kills these two terms. And the choice for A is going to be 4b, okay, 8b, okay, a constant b, n theta over n kappa. If I do it like this guy disappears, but there is an A here. So the error is this. Okay, there is a dependence on b, but at the end you take b to infinity and all the errors disappear. And this A, you see, it goes to 0, but only for theta less than 1. This is where it okay? So now the second replacement lemma for exercise, because I think it's, it's impossible. So I think yes, I didn't have time to talk about this, but anyway. So the second replacement, it was this one. Remember that this is what we need for the case in which we are looking at Dirichlet boundary conditions with test functions which are 0 at the boundaries. So if you want to prove the other one for functions of compact support, it is very similar to this one. So the tricks are basically the same. So for functions of compact support, we need to show this thing. You can replace the average. So if you remember, this is an average. OK, this is here. This is an average in a box at the right of 1 with size epsilon n. And we need to replace this by alpha. This is what we need in order to show that the profile, the third condition at the PDE, to show that the profile is alpha and beta at the boundaries. And to prove this, you do it in 2 steps. First, you show that eta 1 is replaced by alpha. It's done. And now you show, which is the one that we need now for Robin, you show that you can replace this guy by the average. OK? And then that's it. Eta 1. OK, and you show that you combine these two things. So let me tell you how you prove this one, which is exactly the one that we need for the Robin and the Neumann boundary conditions. Remember that in Robin and Neumann, theta is greater or equal to 1. So we are happy because the measure that we can take is the Bernoulli product measure. I erased it. No, it is here. So you see that when theta is greater or equal to 1, the measure that we can take is just Bernoulli constant. So the profile is constant. So we don't have many of the computations that we needed here, to have this price of changing measure. We don't have. The Dirichlet form is nice. And now, the only thing to control, OK, we need some lemma very similar to this one. So Dirichlet forms are controlled. I can take a profile which is constant. So now let me control this term, the corresponding term in here. So I would have to control this term, eta 1. Let me do it with L. And then at the end, I make the choice L equal to epsilon n. So I need to control this term. And I need to bound it by the false Dirichlet form. In this case, you look that I'm changing eta 1 with the average in a box to the right. So what I'm going to use here is not the Dirichlet form coming from the boundary, but the Dirichlet form coming from the bulk. Okay? So the trick is very similar to this one. Okay, I didn't show how you do this, but it is always the same trick. You write this guy. So remember that this is an average, 1 over L, the sum of a y going from 1 to L, eta y. And then you have this, eta 1 minus this guy. You put this eta 1 inside the sum. Okay? So I have this eta 1 minus eta y. And then you write this guy in a telescopic way. So as the sum starting from 1 up to y minus 1 eta z minus eta z plus 1. And then you do the same trick. You just replace variables, and you try to force to see this term here. Ah, this term here, okay, but now you don't know. You remember what this was? This was the square root, maybe not, okay. So this guy is the integral squared d mu. So the idea is that we write down the integral. There is an f. So at this point, this guy which is here is this guy, and the measure is the Bernoulli with a constant profile, okay? So what I do is that I write it as 1/2 of itself plus 1/2 of itself. I change variables, and when I change variables, I will see the f at eta x, x plus 1. So there are some tricks, but basically it is this. And you can show that this thing goes to 0. Then you have to choose the, this, there will be a factor, again, a factor a, and you have to choose a, but comparing it with the bulk generator, okay, the Dirichlet form from the bulk. And you can show that this thing goes to 0 for any theta greater or equal to 1. Okay, so that's that's basically the idea. I'm sorry, this was too technical. I'm exhausted. But it was okay, it was understandable. So basically the idea is this one. Of course, I'm hiding many things. But I mean, to see the boundary conditions, this is the job that one has to do. Even being symmetric simple exclusion, there are many replacements to do. So next to Wednesday, what I'm going to try to show you, maybe I will not do all the technical, but it's similar, is that I'm going to look at the model that I explained in the morning. So it is again the same, so it is again an exclusion, but now jumps can be arbitrarily long, so I can have jumps. In fact, I'm going to have infinite reservoirs. So I'm going to have the following dynamics. So here is the 1, n minus 1. I'm going to add infinite reservoirs to the right, infinitely many to the left, and I'm going to allow particles to jump out to this reservoir or to the other one. And what we are going to see is that depending on the choice of the probability that I put here, if it has finite variance or not, what are the type of boundary conditions that we get? And in one case, we will see that, in fact, we don't get the Laplacian, but we will get the fractional Laplacian. Okay, so that's what I want to do in the next, and I hope you come for Wednesday, that you didn't get exhausted. Okay, so I thank you very much.